turning to the next curve, we want to sketch the curve r equal root 3 over 2 plus sine theta, and we're going to proceed in a similar way to the previous two examples, starting with the study of the variations of the function r as a function of theta. The derivative here is just cosine, and we can look at the sign of cosine from 0 to 2 pi. And cosine is going to be 0 at pi over 2 and at 3 pi over 2. It is positive from 0 to pi over 2, negative between pi over 2 and 3 pi over 2, and positive again from 3 pi over 2 to 2 pi. In terms of variations of the function r, this is what that means. It's increasing from 0 to pi over 2, decreasing between pi over 2 and 3 pi over 2, and increasing again from 3 pi over 2 to 2 pi. I have included here the value at these particular points. When you plug, for instance, theta equals 0 in the function, the sign is 0, so you get r is root 3 over 2. At pi over 2, which is a local maximum for the distance to the pole, the sign is 1, so we get 1 plus root 3 over 2. At 3 pi over 2, the sign is negative 1, so we get root 3 over 2 minus 1, which interestingly is negative. And at 2 pi, we get again root 3 over 2. Now, you see that between pi over 2 and 3 pi over 2, and between 3 pi over 2 and 2 pi, the function r is going to take the value 0, because we go from a positive value at pi over 2 and we decrease to a negative value at 3 pi over 2, and the function r is continuous. So using the intermediate value theorem, we know that somewhere it's going to take the value 0. Similarly, it's going to take the value 0 somewhere between 3 pi over 2 and 2 pi. So we want to know where exactly, because of course when r is 0 we are at the pole, so this is an important point. And it's easy to figure that out. We set r equals 0, that means the sign is negative root 3 over 2. And on the interval 0 to pi, this happens in two places, for the angle 4 pi over 3 and for the angle 5 pi over 3. So we're going to include these values in our table, and r is 0 at these particular values of theta. So now let's try to trace out our curve, starting with the angle 0. Then the value of r is root 3 over 2, so we start out at root 3 over 2, which is about 0.85. So we start with this point, and as the angle increases from 0 to pi over 2, the distance to the pole increases from root 3 over 2 to 1 plus root 3 over 2. And as we continue to turn from pi over 2 to pi, then the value of r is going to decrease from 1 plus root 3 over 2 to root 3 over 2 again, because for theta equal pi, the sign is 0. And so that means we have another side here that is symmetric with respect to the y-axis, which is something, of course, that we can observe from the fact that sine of theta is the same as sine of pi minus theta. Now we can ask, okay, what is the slope of the tangent line here? And we can do that using our formula that dy over dx is given by r prime sine plus r cosine divided by r prime cosine minus r sine. In our case, r prime is cosine and r is root 3 over 2 plus sine. So we plug things in, and now we can plug theta equals 0 in this. And you see that when theta is 0, sine of theta is 0, so the first term at the top is 0. And then at the bottom, the second term at the top, cosine 0 is 1, so we get root 3 over 2. And at the bottom we have 1 for cosine square theta and 0 for the other term, so we end up with root 3 over 2 for the tangent line. So this is the slope of the tangent line at that point. Similarly, we can ask what is the slope of the tangent line at the point corresponding to theta equal pi over 2, the intersection with the y-axis. And if we plug theta equal pi over 2 in our formula, then cosine is 0, which gives us 0 for both terms at the top. and sine is 1, which gives us negative 1 plus root 3 over 2 at the bottom. In other words, we get 0 over something non-zero, so this is 0. Means if the slope is 0, we get a horizontal tangent. Now on that side, we get negative root 3 over 2, as you can expect by symmetry about the y-axis. Now let's continue to turn around from pi to 4 pi over 3. So now theta is going to increase from pi to 4 pi over 3, and r is going to decrease from root 3 over 2 to 0. So we get back to the pole. Now you see that if we continue to turn from 4 pi over 3 to 3 pi over 2, then r is going to become negative. That means that the red point is going to move along the opposite half ray to the one we're pointing in. So first, you should note that theta equals 4 pi over 3 is a tangent line here, because we're going back to the pole, and we've seen that this is exactly what happens. If I go back to the pole for 4 pi over 3, then theta equals 4 pi over 3 is a tangent line. So as we turn, r is negative, and because this value is negative, and we go from 0 to this value. And so we're going to have our red point move in the along the opposite half ray. So if I turn, this is what we see, and the tangent line for that particular point at 3 pi over 2, if I plug in 3 pi over 2 in my formula for the slope of the tangent line, dy over dx, because the cosine is 0, then both terms at the top are 0. Because the sine is not 0, we get a non-zero value at the bottom, so we get again an horizontal tangent at that particular point of intersection with the y-axis. And now if I continue to turn now from 3 pi over 2 to 5 pi over 3, so r now is going to increase from this negative value root 3 over 2 minus 1 to 0. So go back to the pole this way, and then the line theta equals 5 pi over 3 is our tangent line when we come back to the pole. And then as we move back from 5 pi over 3 to 2 pi, r is again positive, so we trace out the curve this way. So we have all our important points, important tangents, and if we smooth things out, this is what we obtain. Now turn to the next video to discuss arc length in polar coordinates.